Lab 2, Advanced Modeling of Charge Tapes. Modeling charge tapes as a collection of charges. In this lab, I generated excess charge in clear tape. I then created a more complex computer model of the situation that models the tapes as a collection of charges instead of a single point charge. Then determined the charge of this one piece of tape using this complex computational model. Note that the code was provided in part by the instructors. The result of this experiment was a tape charge of 7.589 times 10 to the negative 8 coulombs. Excess charge is generated in the tape by layering two pieces of tape one atop the other and then quickly pulling away the top piece. These two charged pieces of tape created this way are assumed to have the same charge and therefore repel each other. This repulsion can be used to float one piece of tape atop the other. The tape floats in a constant position when the electric force is equal to the gravitational force by Newton's laws. The gravitational force is determined using the mass of the tape. The charge of the levitated tape, the tape in question, is determined by iteratively changing it in the code until the value of electric force predicted by the code matches the magnitude of gravitational force. It is important to discuss the specific physics principles in play here. The first important principle is Newton's second law. Net force is equal to mass times acceleration. As the levitated tape is stationary, it can be concluded that it is experiencing no acceleration. Acceleration is zero. By this equation, F net equals ma, the net force must be equal to zero. As the only two forces acting on levitated tape are gravity and the electric force applied by the other tape, the force of gravity in magnitude is equal to the magnitude of the electric force. As gravity is downwards, the electric force must be directed upwards in order for the forces to cancel out and produce zero acceleration. Secondly, the electric field vector can be calculated using the formula 1 over 4 pi epsilon naught times the charge of the source particle divided by the magnitude of their distance times the unit vector that represents the direction pointing from the particle generating the electric field to the point of interest. The electric force can then be calculated by multiplying this electric field by the charge at the location of interest. The final important principle for this model that uses multiple charges to represent the charged tape is the principle of superposition. The principle of superposition is the idea that the combined effects of many charges acting on one point are the same as just taking the sum of each individual electric field generated by each individual charge. That is to say, if we had a bunch of charges all acting on one point, we could take the action of each individual charge and sum up those actions to generate the total electric field, or the net electric field. Furthermore, as the electric force is just the electric field times the charge of the particle at the observation location, we can apply the principle of superposition to electric forces, not just electric fields. The principle of superposition can therefore be used to model the charge tape as a collection of many small charges. By breaking up both tapes into many small charges, calculating the electric field that each one charge applies to each other charge, and then just adding up all of those electric fields, or rather converting them all to electric forces, and then adding up all of those electric forces. Note that it is assumed that the tapes do not apply charges internally, that is to say, particles inside of one tape don't press up against other particles in that one tape, and that the tape behaves rigidly. Additionally, as stated earlier, it is assumed that both tapes have the same total charge. In this staged replication of the experiment, you can see the method used to measure the separation between the tapes in a steady state. Note that the measurement was fairly imprecise due to the fact that the ruler had to be fairly far away from the actual site of the experiment, as the tape was attracted to the metal ruler. Here is the model used to compute the charge on the tape of interest. The model calculates the force due to gravity using the equation Fg equals mass times acceleration due to gravity. As stated before, since we know that magnitude of electric force is equal to magnitude of gravitational force, the charge Q of the tape is manipulated in the code until the outputted calculated electric force is equal to the gravitational force, at least in magnitude. Direction, of course, they are opposite. This electric force is calculated by breaking both tapes up into small charges dq. Then, the force dF applied by each small charge dq to each other small charge dq can be calculated by calculating dE and then turning dE into dF, as shown in the equations. Finally, the total net force can be found simply by summing together all the tiny little forces dF applied by the bottom tape to the upper tape. Because of the complexity of the code, it is inappropriate to present it in this format. However, it is accessible in the video description. The difference in predicted charge between this more complex model and the earlier model from Lab 1 is 3.4 times 10 to the negative 8 coulombs, nearly a twofold increase. This difference is because Although the Lab 1 model represents an adequate model of the system behaves much more like the model we've constructed here. In fact, it would be even more accurate to model the system as a continuous distribution of charges. In short, the Lab 1 model is less accurate than our model here, and therefore this difference in charge represents just an increase in accuracy. Thank you for watching. The link to the code and my merch store is in the video description. Please subscribe if you like the video.